So we're going to kind of go over what we went over. It was day 2 for trees, and we didn't really talk about trees too much because we pretty much covered them. What we're going to do is we're going to take that one lesson. Let's see if I can scoop it up here to show you. Remember this one with Leah flying from Boston to Denver and the luggage making it and all that kind of thing? Well, we're going to go ahead and redo that problem, only this time we're going to do it in a table. Alright, so let's just label this the Leah problem. Let's see, where are we here? There we are. It's the Leah problem done with a table. Alright, so if you remember that problem, it gave us one event A, that the flight was on time. Oh, that looks terrible. Let me fix that. Alright, that the flight was on time. Or left on time, I guess. And event B was that her luggage arrived with her. Okay. All right. So looking at this, there's really two things going on here. Flight was on time or it wasn't. Luggage arrived with her or it didn't. All right. So that's really two things per event. And it's going to be the interaction. So we're looking at A and A complement, B and B complement. These are going to set up 4 joint probabilities. So when we set up a table, we're going to want to have 3 uprights, kind of like this, and 3 horizontals, maybe something like this. And we'll just leave this for a marginal total. Let's make that plural. And this will be totals. And since we're going to be in probabilities, this will have a grand total probability of 1. And let's call this that the flight is on time. That is going to be event A. And this one will be late. I think that was the 2 options. So that'll be A complement. And then we'll put arrives for the luggage, and that'll be the event B. And then B complement is that it doesn't. Okay? All right, well, we know some things that were given in the problem. For example, we were given the probability of A, that the flight was on time, and that was 0.15. We're also, well, we weren't given it, but we can figure out pretty quickly that the probability that it was late was 0.85. So we can use that. We're also given the probability of B, given that A occurred, and that was that the luggage arrived with her, given that the flight was on time, and that was 0.95. And then the probability of B given A complement, given that the flight was late, that the luggage arrived on time, and that was 0.65. So we're going to fill this whole table in given this. And we can start out with the probability of A, that the flight was on time. That 0.15 goes here because there are 2 ways that a flight can be on time: when the luggage arrives with her and when it doesn't. I guess it would be connected with or. So those 2 things should add up to 0.15. There's your probability of A. So since this has to add up to the 1 over here, this is 0.85, which we kind of knew from up here. So that's the probability of A complement. All right? That's all we've got. But we do have these relationships, and we have some formulas. So let's start out. This would be the probability of A and B. This will be the probability of A complement and B. This will be the probability of A and B complement. And this will be the probability of A complement and B complement. Okay? So let's just start out with this probability of A and B. I believe that according to our formula for the general multiplication rule, is the probability of A times the probability of B given A. And we know that. We know the probability of A up here is 0.15. And we know that the conditional probability of B given A is 0.95. And so that's going to multiply to 0.1425. All right? So that goes right here. And since there's two ways that A can happen, and they're connected with OR, that means that this plus whatever this is has to be 0.15. So if you subtract 0.1425 from 0.15, you get this, 0.0075. All right, so that's good. We got a bunch of it filled in. Now we've got to complete one of these lines here, because then the whole table will fill itself in, but we really need one, either this or this. All right, so I believe that we can do the probability of A complement and B. Right? Because we know the probability of A complement, well, it's just the probability of A complement times the probability of B given A complement. Well, we know the 0.85, we know the probability of B given A complement, just multiply those two together. So that'll be 0.85 times 0.65. And that should give you 0.5525. And if you add across, you could get this total, which, by the way, is the probability of B, because there's a B and there's a B. So that's the 0.6950. And I believe that this was really the question we were supposed to answer, right? Remember, we did that down here. All right, so we're not even done with this table, and yet we can already answer the question. So if I subtract this number from 1, I get 0.305. And let's go to 4 places. What the heck? So that's the probability of B complement. And we just have this row left, or this joint probability left. So if I subtract 0.0075 from here, I get it. Or if I subtract 0.5525 from 0.85, I get it. Either way, it should be 0.2975. So again, those joint probabilities should all match up to these joint probabilities right here. And surprise, they do. All right? So we have the individual probabilities B and B complement, the individual probabilities A and A complement. We have the 4 joint probabilities. The only thing we don't have are conditional probabilities. So, but those are readily easy to get to. So let's just say, what's the probability that the flight is on time, given that the luggage arrived with her? Well, that would restrict you to this right here, to this condition. All right, so that would be 0.1425 over 0.6950. So you can do any sort of conditional probability that you want. You can do, well, we were given a couple of them here, this one and this one, B given A complement, but we can switch this, right? We can do the probability of A given B complement, which, or given B rather, which we just did, all right? Or at least I showed you how to do it. So yeah, everything is set up in order for you to get all the joint, which we found, all the individuals, and by extension, all of the conditional, including all the ones that are reversed, which will make it pretty easy. All right. Some people really like the tables. Some people really like the tree diagrams. I personally don't care. Do whichever ones you want. Okay. Now the other thing that we did was, I'm trying to bring us back down to earth a little bit with probability, because in the end, probability is just success over total, right? And we're learning formulas, and sometimes we're not getting them right. So let's just say that we're going to go to a very simple probability experiment. Let's just say you flip a coin, and roll a die. All right, can't get too much easier than that. All right, here's what I want you to do. I want you to find the probability of getting a 6 on the die roll or a head. And that seems like a pretty straightforward thing. However, people missed it all day. So why don't you pause this and see if you can get an answer. So 5, 4, 3, 2, 1. Okay, if you said 2/3, you are not right, okay? Because this is the probability of a 6 plus, remember or means plus, probability of a head. But can't you get a 6 and a head at the same time? So this is not a disjoint situation. So you've got to subtract the probability of a 6 and a head. And I bet you forgot that. All right, so this will be 1 over 6 plus 1 over 2 minus 1 over 6 times 1 over 2. And this is probably what you forgot, because this will be, if I convert everything to over 12, this will be 2 over 12 plus, what's that, 6 over 12? And there's your 8 over 12, or 2/3, but you have to subtract 1 over 12, right? So you should have gotten 7 over 12, which I believe is, 0.5833 repeating, okay? Now, look, this is what I did. I just proposed this as an alternative. Can you write out the sample space? I mean, would you be that opposed to doing it? So let's go ahead and just do it. And you'll see how easy this is to answer. So head and a 1, head and a 2, head and a 3. It does take a moment to write it out, but it's not forever. Oops, get rid of that, especially if you write it wrong. All right, so this will be a head and a 5. Hang on. Head and a 6. And then you got the same thing with a tail. So tail and 1, tail 2, tail 3. Sorry, don't need to call out everything I write. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 events. So your total is 12. And let's just circle everything here that's either a head or a 6. So it's a head and a 1. There's head, 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 and a 6. That's 7 out of 12. See how easy that was? And all it is success out of total. Now the problem with you maybe getting 8 over 12 or 2/3 is that you counted the head and the 6 once when you counted up the heads, but then you counted it a second time when you counted up the 6. So that's why you had to subtract that product, that joint probability, in order to get the right answer. Okay? So don't feel like you're being some little ridiculous kid if you're doing something like this. This is a valid way to get probabilities. All right? So we also went over the first homework problem in the book, number 40. It's a pretty crazy problem. I'm not going to do it here, but you can ask about it tomorrow. And yeah, so that's pretty much what we went over. The rest of the time was set aside for working. So I'm going to allow you to leave and set aside this time for working. So I will see you tomorrow.